Welcome back. Today we begin our discussion of Chapter 3, and the first section in Chapter 3 is an introduction to paired data and scatter diagrams. Let's begin with an example about watermelons. From a large watermelon field, 30 vines are chosen at random. After 8 weeks, the watermelons are removed from the vines and the average weight of the watermelons from each vine is determined. Then each plant is carefully dug up and its root depth is measured. So we have two variables here that we're considering. We're considering root depth, but we're also considering the average weight of the watermelons. And we'll generate a data table from this. And here are our 30 watermelon vines. First one that we looked at had a root depth of 26.7 inches, and the mean weight of the watermelon, 20.3 pounds. And we continue on. A 14-inch root yielded a watermelon with a weight of 4.8 pounds on average, and so on all the way down the first column, and then here's 10 more, and then here's 10 more. When we go to plot this data, we find that it doesn't fit a straight line. Yeah, there's a straight line drawn in there, and I'll talk about that in a minute. But you'll notice that there are a lot of points that are above the line, there are a lot of points that are below the line. There is a general trend here you might have noticed. We'll come back to the idea of trends again in a moment. But again, these points are not linear. There's no way to connect all of the points with a line. The line that we drew in there is what's called a best fit line. And we're drawing that to indicate a general trend of the data. In Algebra 2, you might have heard this taught as draw the line so that it is as close as possible to as many of the points as possible. And that's a wonderful way for us to handle it in algebra class. In statistics, we want a little bit better method, and that's one of the things that we'll look at in this chapter. And we can answer the question, what is it about this line that's drawn here that makes this the best fit, or at least a very good fit for the data? All that's coming up in the next couple of lessons. But in a general sense, the question is, how well do the points of the scatter plot fit any line? The closer the points are to forming a line, the greater we say their correlation is, or specifically their linear correlation. If we're trying to find a line, we call it linear correlation. In the ideal case, the points form a line perfectly, and we would call that perfect linear correlation. We're not typically that lucky. So it probably is going to be that there are some other points out and about here in different places, and you see me drawing in some points here, and I want to get rid of some of these further ones. So what I've drawn now in the picture on the left is no longer a perfect linear correlation. There are points that are not on the line. We would call this a strong linear correlation. That it's pretty close. It's not there, but it's close. And there's an obvious trend. When the slope of the best fit line is positive, we say that there is a positive correlation. So in the diagram on the left, we are saying that we have positive correlation. In the diagram on the right, X and Y are negatively correlated. As X increases, Y is decreasing. Whereas in the left, as X went up, so too did Y. So we've talked about a perfect linear correlation and a strong linear correlation. As the points drift further and further away from being a line, we go from perfect to strong to what we would call a moderate linear correlation. You can see a trend here. Even if it's not a blatantly obvious trend, there's a trend going on here. In the picture on the left, it certainly appears that, speaking generally of the data points, that as x is increasing, y is increasing with it. And then on the right, as x increases, y is decreasing. And sometimes we get no linear correlation, and it might be that the points are forming some kind of a shape that that most definitely isn't a line. There are other types of correlation. We could fit the data points here on the left, perhaps could fit them into something that looks like a parabola from algebra class. We don't cover that here. In this course, we're only interested in linear models. And in the case of the one on the right, good luck drawing anything that's going to come close to connecting all the points unless you decided you wanted to scribble them all together. You draw a scribble and say, hey, look, I did it. Now, that doesn't work. It certainly doesn't work when it has to be a line. There's no way you are going to draw a straight line that comes close to either, to all of the points, or most of the points, either in the one on the left or the one on the right. Let's describe correlation here. We have a new problem where we are comparing the number of work hours of safety training, that'll be our x, versus the number of work hours that are lost due to accidents, y. One would hope that as x increases, as the number of safety training hours increases, that the number of hours lost to accidents, y, would decrease. And that is, at first glance on the table, that certainly appears to be what's happening here. But we need to plot it to be confident of that. At least for right now, we need to plot these points in order to be confident in our conclusion. So let's take this data table and plot the points and describe the general relationship between the work hours of safety training and the work hours lost due to accidents. Here's our graph. Would a line reasonably fit this? And what would that line look like? Yeah, we could probably draw a line of best fit here that would be reasonable, and it would probably have a shape like this, roughly speaking. So we're getting pretty close to all of the points. This is a line with a negative slope. And since we have a negative slope, we will say that x and y are negatively correlated. That as x increases, y decreases, which is exactly what we would expect to have happen here. Next time out, we'll be writing an equation for this line based on the data itself. See you then.